Dare I sing? I dare. Me. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. The quadratic formula is beautiful. My singing, not so much. But what is the quadratic formula for? Given a quadratic equation, ax squared plus bx plus c equals 0, where a, b, and c are constants, the quadratic formula tells you the solutions. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. The song can help you remember it. But why does it work? Algebraically, it's based on the method of completing the square. Geometrically, it's based on transformations of graphs, and that's one of our main topics here in lesson 1.3 of Calculus 1. Let's think about this in the context of an example where we graph a quadratic function without technology. Now, while we certainly could just plot points, our goal will be to complete the square, both to find the x-intercepts of the function and to think of it in terms of transformations. We want to make a graph of the function y equals f of x equals 3x squared minus 12x plus 9, called a quadratic function because it's a polynomial whose highest power is 2. Again, the method is to complete the square. This method can be given a geometric meaning related to literal squares. However, we'll approach it purely algebraically. If the coefficient of x squared is something other than 1, such as 3, factor that number out of the first 2 terms, even if you have to work with fractions afterwards. In this case, after factoring the 3 out, you're left with x squared minus 4x inside parentheses. The plus 9 stays as is. Next, take the coefficient of x, in this case negative 4, divide it by 2 to get negative 2 in this case, square that number to get positive 4, and then add that number inside the parentheses, like this. However, because you've added 4 inside the parentheses, you really added 3 times 4 to the overall expression, so you have to compensate by subtracting it off. If you've done it correctly, the expression inside the parentheses will be a perfect square. In this case, x minus 2 quantity squared. You should also simplify 9 minus 3 times 4 to equal minus 3. What then are the intercepts of this function? We can find the x-intercepts by setting the function equal to 0. We want to find the values of x where y equals 0. Use the formula we obtained after completing the square. Replace f of x with 3 times x minus 2 quantity squared minus 3 and set it equal to 0. The benefit of this is that we can do a couple of quick algebra steps to isolate an expression that is squared. We can then take the square root of both sides, allowing for both possible square roots of 1, plus or minus 1. After adding 2 to both sides and simplifying, we obtain the 2 x-intercepts, x equals 1 and x equals 3. The logic here is that if f of x equals 0, then x is 1 or 3. But you should also double check that f of 1 and f of 3 do indeed equal 0. The y-intercept is easy. Just replace x with 0. Find f of 0. We can use the original formula to get a y-intercept at y equals 9. It's worth taking a moment to see that the quadratic formula gives the same answers for the x-intercepts. Once again, we set f of x equal to 0 and solve for x. But now use the original formula for the function f of x. Set 3x squared minus 12x plus 9 equal to 0. For the quadratic formula, a equals 3, b equals negative 12, and c equals 9. Therefore, x is equal to negative of negative 12, which is positive 12, plus or minus the square root of negative 12 squared, which is 144, minus 4 times 3 times 9, all over 2 times 3. This simplifies to 2 plus or minus the square root of 36 over 6, which is 2 plus or minus 1, which gives 1 and 3 as the x-intercepts. So far then, we know the graph of f of x contains these 3 points. The 2 on the x-axis are the x-intercepts, and the 1 on the y-axis is the y-intercept. If you also happen to know that the graph of a quadratic is a parabola, you should be able to give a rough sketch of the graph right now. Pause the video and give it a try. But now, let's take a systematic approach using transformations. Let's also assume we know what the graph of g of x equals x squared looks like. It's a parabola opening upward, it's concave up. Its lowest point, called the vertex, is at the origin 0, 0. You could also say that the vertical y-axis is an axis of symmetry. making this function what's called an even function. What we want to do now is to see how this graph can be stretched and translated to obtain the graph of our original function f of x. The formula for f of x that we obtained by completing the square will be essential. Since the leading coefficient of the function f of x was 3, let's start by transforming g of x equals x squared into another function, h of x equals 3 times x squared. The graph of h is obtained by stretching the graph of g vertically by a factor of 3. For any given point on the graph of g, the corresponding point on the graph of h has a y-coordinate 3 times as far from 0. That's because for each value of x, the output of h is 3 times the output of g. Notice that the low point of this new graph, the vertex of the parabola, is still at the origin. For any real number x, the output of h can never be negative, and takes a minimum value of y equals 0 when x is 0. Also notice that for each value of x, the slope of h is 3 times the slope of g. That's a very important fact for calculus. Since the formula for f of x after completing the square involved x minus 2 quantity squared, let's transform h of x into another function, call it j of x, by replacing x with x minus 2. This has the geometric effect of translating the graph of h to the right by 2 units to get the graph of j. Notice the vertex goes from the point 0, 0 to the point 2, 0. Indeed, this function is minimized when x equals 2. That's when the output y equals 0. In fact, the value of j at any given value of x is the same as the value of h at x minus 2, and x is 2 units to the right of x minus 2. Also notice that since this is a rigid translation, the slope of j of x at a given value of x is the same as the slope of h at the value x minus 2. This is again something that is important for calculus. Finally, to transform j of x into our original function f of x, we have to subtract 3, because the formula for f of x after completing the square had another minus 3 attached. This has the geometric effect of translating the graph of j of x down by 3 units to get the graph of f of x. For any given value of x, f of x is j of x minus 3. Each output is 3 units lower. The vertex gets translated from the point 2, 0 to the point 2, negative 3. And for each value of x, the slope of the graph is the same, because this is a rigid downward translation. Also notice that the intercepts are in the correct spots. The x-intercepts are 1 and 3, and the y-intercept is 9, just like we found before. Let's now generalize what we've done for quadratic functions, completing the square, and transformations. The standard form of a general quadratic function is y equals f of x equals ax squared plus bx plus c, where a is assumed to be non-zero because otherwise it wouldn't even be a quadratic. A is called the leading coefficient of the quadratic. It's related to the concavity of the graph. When a is positive, the graph is concave up, and when a is negative, the graph is concave down. That also means that when a is positive, the vertex of the parabola is the lowest point on the graph, and when a is negative, the vertex of the parabola is the highest point on the graph. The value of a also affects how thin or wide the graph of f is. The farther a is from 0, the thinner the graph is. The closer a is to 0, the wider the graph is. b is the coefficient of the first power of x. It's related to the slope of the graph at x equals 0, though we need to rigorously define what that means. Here, suffice it to say that when b is positive, the graph of f is increasing near 0, and when b is negative, the graph of f is decreasing near 0. In fact, when b equals 0, the graph of f has a vertex at x equals 0. Finally, the value of c is in fact the y-intercept of the function because it is the value of f of 0. This is the location of where the graph of f crosses the y-axis. What's the general approach for completing the square? Let f of x equal ax squared plus bx plus c. The coefficient of x squared is a, which we're assuming to be non-zero. Factor it out to see that f of x can be written as a times the quantity x squared plus b over a times x, then plus c. Now do the same thing as before. Take the coefficient of x inside the parentheses, b over a, divide it by 2 to get b over 2a, then square that fraction to get b squared over 4a squared before adding that expression inside the parentheses. Since there's also an a outside the parentheses, we need to compensate by subtracting a times b squared over 4a squared, which simplifies to b squared over 4a. The expression inside the parentheses is now a perfect square, and the expression outside the parentheses can be simplified by getting a common denominator. After factoring and combining, we get this form for the function. F of x equals a times the quantity, x plus b over 2a quantity squared, plus the fraction 4ac minus b squared all over 4a. This is called the vertex form of this quadratic function. The reason is because it will help us find the vertex of the graph. But for the moment, let's see how it helps us derive the quadratic formula. Set this quadratic in vertex form equal to 0 and solve for x. Subtract the fraction from both sides, obtaining this equation. Divide both sides by a to get this equation. Take the square root of both sides, allowing for a plus or minus square root on the right. Then subtract b over 2a from both sides and combine the fractions. You get the quadratic formula. Take a moment to just savor its beauty. You might wonder though, what happens if b squared minus 4ac is negative? I'll let you think about it. That's the algebraic approach. How about the general approach involving transformations? Start with the basic function g of x equals x squared. Multiply this function by a to get h of x equals a times g of x equals a times x squared. You could call this a vertical dilation. If a is bigger than 1, this dilation stretches the graph in the vertical direction. If a is between 0 and 1, it compresses the graph in the vertical direction. And if a is negative, a reflection across the horizontal axis also comes into play, where the absolute value of a determines whether it's a stretch or a compression. Next, create a function j of x from h by replacing x with x plus b over 2a. Because h of x equals ax squared, that means j of x equals a times x plus b over 2a quantity squared. This is a horizontal translation. If b over 2a is negative, it's a translation to the right because adding a negative number is the same as subtracting a positive number. And if b over 2a is positive, it's a translation to the left. In either case, the amount of the translation is the absolute value of b over 2a. Finally, we obtain the function f of x by adding the constant 4ac minus b squared all over 4a to the function j of x. This is a vertical translation, upward if the fraction is positive and downward if the fraction is negative. This shows how the original function in vertex form can be thought of in terms of transformations. We can also use this sequence of transformations to follow the vertex. For the function g of x and the function h of x, the vertex is at the origin, 0, 0. For j of x, the vertex has been translated to have an x-coordinate at negative b over 2a and a y-coordinate still at 0. And for f of x, the vertex still has an x-coordinate of negative b over 2a, but now it has a y-coordinate equal to the fraction 4ac minus b squared all over 4a. Make sure you think about why this all makes sense. To summarize, in general, for finding the vertex, if we have the quadratic in vertex form like this, the vertex will have these coordinates. This will be a low point or minimum if a is positive because the graph of f will be concave up, and a high point or maximum if a is negative because the graph will be concave down. It turns out that all these ideas are related to another very important concept in calculus called function composition. This is where we are applying functions sequentially as a step-by-step process. For example, the function f of x equals 4x squared can be conceptualized in 2 steps as follows. First, square x to get x squared, then multiply that quantity by 4 to get 4x squared. The order of operations, as always, is essential. If instead we had multiplied by 4 first before squaring, the function would ultimately simplify to 16x squared. It would be a different function. How do we define function composition in general? Suppose h is a function defined on some domain a, which could be a subset of real numbers, and g is another function defined on some domain b that happens to contain the range of h, meaning the set of all outputs of h. Then we can define a new function f, written as g circle h or g compose h, by applying h first, then g. In the diagram, this is visualized going from left to right, but with the g compose h notation, we work from right to left. And we write that f of x equals g compose h of x equals g of h of x. The number x gets plugged into h first, h is the inside function, and then h of x gets plugged into g. G is the outside function. We work from inside to outside, equivalently from right to left. Sometimes, especially in applications of calculus, this is thought of in terms of a new variable. That new variable might represent some other real-life quantity. Here we'll call the new variable u. U equals h of x and y equals g of u. If we replace u with h of x, we get that y equals g of h of x. G compose h of x. Let's go back to the 4x squared example. Our function is y equals f of x equals 4x squared. We'd like to write this as the composition of 2 simpler functions. The operation that gets done first is x squared. After that, we multiply by 4. Our inner function that gets done first is u equals h of x equals x squared, and our outer function that gets done second is y equals g of u equals 4 times u. When we compose these, we get y equals g of u equals g of h of x. H of x is x squared, so that's the same as g of x squared. In the formula for g, replace u with x squared to get 4x squared. This is g compose h of x. On the other hand, we could ask what happens if we change the order that these functions are composed. What happens if we compute h compose g? Ignoring any inconsistencies with variable names, which don't really matter anyway, we could write h compose g of x equals h of g of x, replace g of x with 4x. Since h represents the squaring function, that gives 4x quantity squared, which simplifies to 16x squared, which does not equal g compose h of x. Therefore, we say that function composition is not commutative. G compose h does not equal h compose g. The order of the functions matters. In other words, the order of the operations matters. Let's work through another example. Let y equal f of x equal e to the 3x. I'd like to write this as a composition. You might even say I'd like to decompose it. Think about plugging numbers in for x. When you plug a value of x in, you first multiply by 3, and then you exponentiate. You make that number the power of e. In other words, the inner function is h of x equals 3 times x, and the outer function is g of u equals e to the u. You can double check this in the same way as before. Y equals g of u, u gets replaced by h of x, which is 3x. G of 3x is e to the 3x because ultimately u gets replaced by 3x. This is g compose h of x, and it's the same as the original function f of x. On the other hand, once again, h compose g of x is something different. H compose g of x equals h of g of x. G of x is e to the x. Don't let the change from u to x bother you. Since h of a quantity is 3 times that quantity, this becomes 3 times e to the x, which is different than f of x. Once again, g compose h does not equal h compose g. Function composition, in general, is not commutative. It's important to emphasize that function decompositions are not unique. Going back to our first example, f of x equals 4x squared, we can also decompose this with an inner function h of x equals 2x and an outer function g of u equals u squared. Take the time to pause the video and check these details to confirm it. For our second example, f of x equals e to the 3x, an alternative decomposition goes like this. The inner function is h of x equals e to the x, and the outer function is g of u equals u cubed. Here again are details that you should take the time to confirm. It's also important to emphasize that sometimes functions do commute under function composition. For example, if f of x equals the square root of x and g of x equals 1 divided by x, then we see that g compose f of x is g of f of x is g of the square root of x is 1 over the square root of x, and we also see that f compose g of x ultimately simplifies to the same thing. Though we do need the fact that the square root of a ratio is the ratio of the corresponding square roots to confirm this equality. This can all be related to transformations for our quadratic example with multiple compositions. Our quadratic function was f of x equals 3x squared minus 12x plus 9, which we saw by completing the square was equal to 3 times x minus 2 quantity squared minus 3. If we let g of x equal x squared, h of x equal x minus 2, j of x equal 3x, and k of x equal x minus 3, then we can build f of x with a composition of these 4 functions. G of h of x equals x minus 2 quantity squared. Graphically, this takes the graph of g of x and translates it to the right by 2 units. J of g of h of x equals 3 times x minus 2 quantity squared. This takes the preceding graph and stretches it vertically by a factor of 3. Finally, k of j of g of h of x equals the original function f of x. This takes the preceding graph and shifts it down by 3 units. You should take the time to check this. Let's end lesson 1.3 of Calculus 1 with an application of quadratic functions to physics. The application is to free fall under the influence of gravity with no air resistance. We're going to assume that this quadratic function h equals f of t equals negative 4.9 times t squared plus 39.2 times t plus 98 represents the height h of an object in meters above the ground as a function of time t in seconds. The negative 4.9 leading coefficient is the negative of the acceleration due to gravity near the surface of the Earth, 9.8 meters per second divided by 2. The 39.2 coefficient in front of the t is the initial upward velocity in meters per second. This object is moving upward at time 0. And the constant term, 98, is the initial height in meters. It's like this object starts from the top of a tall building. We have three things to do. First, find when the object hits the ground. Second, determine how high the object goes. And third, graph the function and interpret these answers graphically. Here are the solutions of these free-fall questions. To find the time when the object hits the ground, set h equals f of t equal to 0. That means this quadratic equation must be true. Now use the quadratic formula. Here are the details. T equals negative 39.2, which is negative b, plus or minus 39.2 squared, b squared, minus 4 times a times c. A is negative 4.9 and c is 98, all divided by 2 times negative 4.9. That is, all divided by 2a. When you simplify this with your calculator, you get 4 plus or minus 6, which is negative 2 and 10. We want the positive root since we're starting at time 0, so the answer is t equals 10 seconds. Being a quadratic function with a negative leading coefficient, the graph will be concave down and its vertex will be a high point. The object will reach a maximum height at the vertex of the graph. Remember, the vertex occurs when the independent variable has a value equal to negative b over 2a. In this case, that simplifies to 4. Plugging t equals 4 into the function gives a maximum height of 176.4 meters. Pause the video and take the time to double check these calculations. Here's the graph. It is an upside down parabola. The object itself is along the vertical h-axis, going up and reaching a maximum height of 176.4 meters when t equals 4 seconds, corresponding to the vertex on the graph. When it comes down, it reaches 0 when t equals 10, corresponding to the intercept of the graph. When t is bigger than 10, the model and graph are no longer valid. Thanks for watching Lesson 1.3 of Calculus 1.